Okay, we're starting, I think, it's chapter 16, the senses. And it's really a big, important, and fascinating chapter, I think. And there's going to be some really strange things happen in your senses that go against everything you learned about nerves. It's really odd. But anyway, let's get down to the basics. So talking about sense organs. The sense organs do they detect a certain stimulus, a force, some type of energy, whether it's light, sound waves, a taste, pressure, pain, whatever, the detection of some sort of force. And so sensation is a conscious or unconscious awareness of a stimulus. Remember, some of the senses, we're talking about visual senses, like what the pH of your blood is or your blood pressure. We're not talking about that now. We're talking about the conscious senses, the senses that you can detect, that you are aware of, the sensations that you are aware of. Okay. And what we have to do, what sense organs have to do is convert that stimulus, whatever the force is, whether, like I said, whether it's distortion of a membrane, whether it's sound waves, whether it's a chemical stimulus, light stimulus, it has to convert it into action potentials. This is called transduction. Conversion of stimulus into action potentials. Because after all, as we were saying, I think I said this before, what does your brain get from the environment? Does it get sound waves? Does it get chemicals? Does it get light? Does it get pressure? No, it gets action potentials. So we have to convert whatever the stimulus is into action potentials. To convey 4 types of information. 1, modality. That is, what sense is it? What kind of energy is it? Is it light? Is it pressure? Is it sound wave? What is it? And where is it coming from? What part of your body was it coming from? Or what part of your body is being affected? Intensity, how intense is the stimulus? How loud is it? How bright is it? How strong is it? And duration, how long does it last? And that's going to be conveyed by different aspects of action potentials. Okay, so receptors as transducers. And so they have to convert some kind of energy into a receptor potential, in a graded potential. That's going to be converted to an action potential that's going to go into your central nervous system and go to a particular place. So we have to convert it into first a graded potential called a receptor potential. Okay. And so there's modality-gated ion channels. What does that mean? That means opening up ion channels. In order to produce a graded potential, you got to open up ion channels. How do we open up ion channels? Well, there's a bunch of ways to open up ion channels. We talked about voltage-gated ion channels in conduction and action potential. There's also chemical-gated ion channels. There's light-gated ion channels. There's barrel receptors or distortion of membrane, mechanoreceptors that open up ion channels. I'm going to show you in a moment how distortion of a membrane can open up ion channels. So the receptor potential is generated by the opening up of these ion channels. And that is going to go to like a trigger zone, just like an axon hillock. And this is where they're going to be voltage-gated ion channels. And that receptor potential is going to initiate, it's going to bring that part of the membrane to threshold where the voltage-gated ion channels are, and that'll generate an action potential. Okay, where the action potential goes carries the modality information. What is it? Like I said, your brain only sees action potentials. So how does it distinguish between vision, taste, pressure, pain, whatever? Where it goes in the brain. Label lines into the brain. Sight back here, sound here, smell up in the insula. Where does it go? touch the somatosensory cortex, right? That's how it knows. It can tell what the different senses are. Where does it go in the brain? The size of the receptive potential dictates the frequency of action potential. So a small receptive potential will stimulate action potential, say of 10 per second, right? A frequency or hertz of 10 impulses per second. Stronger inputs, a louder sound, a brighter light, a stronger press will generate a larger receptive potential. This will lead to a higher frequency of action potentials, like 100 per second. And so that's intensity info. What is the frequency of action potentials going into the central nervous system? Tells your brain how intense this stimulus is. Okay? And we're going to get into duration in a little bit when we talk about tonic receptors and phasic receptors. Okay, receptive field. Location info. Smaller fields, more precise info. So we'll talk mostly, best example is the skin for touch. The smaller fields, more precise info. And we talked about this. Also, what did we talk about? Oh, we talked about the sensory homunculus. Why is it distorted? Why is there more represented of your fingertips than of your back? Well, it's because, for one reason, there's smaller receptive fields on your fingertips. There's a receptive field. What does that mean? That means the area of skin that's serviced by one sensory neuron, all right, and one sensory touch receptor, okay? On your back, there's a larger receptive field that is serviced by one sensory receptor. And you can tell that by the two-point discrimination test. You take these 2 points, you put them a certain distance apart. You put them on a back, the person can't see them, and you put it on that, and you ask the person, is that 1 point or 2? And they usually say it's 1, even though it's 2. Because both points are hitting in the same receptive field, this large receptive field. And therefore, they're serviced by one sensory neuron. So it feels like one touch. But in a smaller receptive field, you put it on a fingertip, and you don't let the person see it, you put it on a fingertip. Now, is that 1 or 2? They'll say, oh, okay, that is 2. Why? Because the smaller receptive field meant that the 2 points hit in different receptive fields and stimulate 2 sensory neurons rather than 1. And so your brain recognizes as, oh, that's 2 touches, not just 1. Okay, as I said, location info, label lines into the brain. Where does this information go in the brain? All right. Duration info, as I mentioned, phasic and tonic receptors. Phasic receptors are receptors that, if they get the same stimulation, the same intensity, for a long period of time, they'll stop responding, and you won't even get a response. That's called adaptation. Tonic receptors are constant all the time. Doesn't matter whether the stimulation stays constant or not. What the intensity is, it's always it's constant. You will always detect it. In the phasic receptors, why should you have the phasic receptors? Well, remember, your brain thinks that things that change are important. All right. And as we talked about before, the big guy doesn't need to know all about this sensory information that's coming in. If nothing's changing, it's not important, right? And so you don't even send it on to the big guy. You know, everything goes to the thalamus, remember? All the sensory information goes to the thalamus except for olfaction and one pain pathway. So thalamus decides what to go on. But even the sensory receptors will adapt, and they won't even send information to the thalamus anymore if the response is the same. And this is true for, I mean, sometimes you can be holding this glass of water, a glass of whatever, and you're at a party and you get really animated and you think, and you get really talking to somebody, all of a sudden the glass falls out of your hand. And because you put the same pressure on the glass, and after a while, you didn't even feel like you were holding it anymore. Or, like I always used to say, I used to live in Maine, and every small town in Maine stinks like hell because there's a paper plant there. And it smells, I mean, you can smell the towns from miles away. But when you get there and you drive past the paper mill, there's houses right across your street. So how can they stay in that smell for all the time? Well, the smell never changes. They're not even detected anymore. They've adapted to that smell. If you stay in a town long enough, you're not going to smell it anymore as long as it stays the same level. It's also good for good smells as well. You go into a ponderosa pine forest out west and it smells like juicy fruit. Oh, it's a great smell, but you stay in that forest long enough, you won't smell it anymore. Your olfactory adapters are phasic and they will adapt. Okay, so example of a tonic receptor is equilibrium and proprioception. Doesn't matter, I'm balanced, I can stay in here all day and I'm not gonna fall over because my equilibrium receptors, we'll talk about those are in your ear, they're always, they're tonic, they're always fun. And proprioception, I can do this all day because they're always telling your brain where your muscles are located or how contracted your muscles are. But phasic adaptation to a constant sensory stimulus, true for touch, vision, olfactory, and I think also audition, which is hearing. They adapt to a constant intensive stimulus. Sounds like vision wouldn't be one of them because you'll always be able to see, right? But we'll talk about later on about how that point of focus moves around different photoreceptors, and the photoreceptors do adapt, but the image is moving onto new receptors, and that's why you can still always see. So there's tonic receptors and phasic receptors. As I said, here's the stimulus right here, response, stimulus, response, stimulus, response. Same stimulus, same response. Phasic receptor stimulus, you get a response, you get another stimulus, it stays the same, it eventually just goes down and to nothing. You won't detect it anymore. This is, like I said, this is called adaptation. Okay, classification receptors. You can classify them by various means, by stimulus modality. Or do they detect temperature, thermoreceptors? Do they detect light, photoreceptors? Do they detect noxious stimuli like pain, nociceptors? Do they detect chemicals, chemoreceptors? Or do they detect distortion of membrane? And that's mechanoreceptors or baroreceptors. Origin of stimulus. Where is this stimulus coming from? Inside the body or outside the body? Outside the body, exteroreceptors. Inside the body, interoreceptors. So you can have nociceptors that are interoreceptors. You get pain in a particular organ, you're getting it from inside your body. And proprioception is a different, even though proprioception is inside your body, it's given a special category of proprioception from the muscle spindle fibers in your muscles. All right. By distribution of receptors, where are the receptors located? Are they located throughout your body? Those are called general receptors or somesthetic receptors. And we're talking about touch, pressure, temperature, pain, right? Or are they distributed around your head? Those are called the special senses or special receptors. And of course, we're talking about vision, hearing, taste, smell, those are all special senses. And even though you can feel touch on your face, it's still a general sense, even though it's in your face, because it's all over your body. Right? And any given receptor can be classified according to each of the three criteria. Receptor distribution, where's it located? Stimulus origin, outside, so like a touch receptor on your side. A receptor distribution, general, stimulus origin, outside, stimulus modality, distortion of membrane, mechanoreceptor, you see? Receptor distribution, in your eyes, photoreceptors. Stimulus origin from the outside, stimulus modality, light. So receptor distribution for vision is special sense. Stimulus origin, outside, stimulus modality, light. So you can, any given receptor can be classified using those three criteria. Okay. General senses, receptors. Okay, these are all touch receptors or pressure receptors. And there's a whole bunch of different kinds in your skin called the free nerve, Merkel disc, hair at the base of hairs. This is called Meissner's corpus, cross-end lobes, Pacini corpus, Ruffini corpuscles. They're all touch or pressure or pain, and they're all mechanoreceptors. An example is a Pacinian corpuscle, and I'm going to explain how one of those works right here. I think the next, wait a minute. Well, let me go to the next chapter and show you where they are. They're right there in the skin. You know, they're all really touch receptors. So we'll look at more closely a Pacinian corpuscle, which is a type of lamellated corpuscle, and how this works and how does it lead to a receptive potential. Okay, so in here is a nerve ending. Right here, the nerve ending, and it's got mechanically gated ion channels. That is, if the membrane is distorted, this will open up ion channels, particularly sodium ion channels. Sodium channels will be opened up. So, if you press down on this, you indent this a little bit, you indent that a little bit, you indent that a little bit, you indent that a little bit. So this is indented, this is indented, this is indented, and this is indented. This causes sodium ions to rush into the membrane. This causes a receptor potential to travel here. It also travels here, but it's a dead end over here. It travels over here, and here is a trigger zone, right here. Voltage gated sodium and potassium ion channels. So once this graded potential gets here, if it's big enough, it will bring this part of the membrane to threshold. And those are voltage gated ion channels. Sodium will rush in, potassium rushes out, and we got an axe potential. And it travels this way. Through a first order sensory neuron, into the spinal cord, and eventually to the brain. And this thing right here, this graded potential, is a receptor potential. So this is how a touch receptor works. It's mechanically gated ion channels. Okay. There's a whole bunch of different types. You don't have to know the name of all of these types. And also in skin are nociceptors. They are really like free nerve endings, and they're the pain receptors. When you slice into them, that's how you feel pain. We'll get into pain in a bit. So pain is a general sense because it's all over the body. Okay. Let's go back to screen sharing here. Let me go back one. So remember, projection pathways. Now for each one of these senses, we're going to be talking about projection pathways. And that means where it starts to where it ends. It could start anywhere and ends up in the brain, okay? And we've already talked about this in the spinal cord chapter, about sensory pathways having first, second, and third order neurons. All of these have 3 neurons going there, except for proprioception has 2, and we're going to learn out that audition, hearing actually has 4. So there's the exceptions. Okay, pain. This is general sense, like I said, because it's all over your body. The receptors are nociceptors. And you can usually figure out where it's coming from, but there's something called referred pain. And it's something that's interesting. Referred pain is actually coming from somewhere, and oftentimes it's internal. It's interoceptors that are going off, and it feels like the pain's coming from someplace else. And the best example of a heart attack. The pain from a heart attack seems to be coming from your throat and upper shoulder and down your left arm. That's the pain of a heart attack. And it's called referred because somehow there is a crossover between pain, because the pain coming in from your heart goes to the same spinal nerve as the sensations from your arm. And somehow, usually there's no crossover between nerves, but apparently there is some. And so pain up here and down your left arm is a heart attack. Pain right over your heart, that's heartburn. That's much less serious. And somatic and visceral. So remember, somatic pain is pain that you can detect, and visceral pain is pain you can't detect. And but your body recognizes this as a nociceptor and can do things to take care of it. I'm not sure what, but anyway. Okay, so there's a hunk of skin. Okay, so pain projection pathways. To the cerebral cortex by way of the reticular formation, thalamus, and collateral to the limbic system. So here, so pain is going to go through the thalamus, just like every other sense except olfaction. None of olfaction goes through the thalamus. But there's one collateral pain that will actually bypass the thalamus and go to the limbic system. And this is for emotional responses to pain. And they will both go to the cerebral cortex. All right? And so the collateral to the limbic system bypasses the thalamus. That's what I'm saying. There's one pain pathway that actually bypasses the thalamus. And then there's an interesting thing called CNS modulation, or the natural analgesic pathway, also known as spinal gating. The cerebral cortex and the hypothalamus send info to the central gray matter of the midbrain, which projects into the raphe nucleus of the medulla oblongata. And what this is going to be is actually a lessening of pain. So here's the thing. There are some people actually, there's a condition where you don't, where you don't, some people don't feel pain at all. It's a very rare condition. Think of what it's called. Well, they don't feel pain. They don't feel pain at all. And you think, wow, that'd be a great thing. We'll never to feel pain. But they live a really circumspect, very careful, dangerous existence, because pain is really important. I mean, pain tells you there's something wrong, right? And you're going to go do something about this. If you get pain from a joint, you stop using it so much. Pain goes somewhere, you stop using that part of your body, and you let it heal. So pain is a really important signal. But here's the thing. When it first happens, if you're first injured, the pain is like really sharp, and it could be really intense and sharp. Ooh, something really bad just happened. But then that will ease a little bit over well, maybe seconds, maybe just a few minutes. It'll ease from that sharp, intense to like a dull ache. I know when I screwed up my knee in Morocco, the pain was intense when it first happened, and I'm lying on the floor in intense pain. And then in a couple of minutes, it just relaxed to a dull ache. I can move and go get some help. That's the natural analgesic pathway at work. First, let's look at the projection pathway. Okay, so here, you step on you push a finger on a tack, you get pain on the first order nerve fiber into the spinal cord. Pain decussates. Remember, these sensory pathways always decussate either in the spinal cord or the medulla oblongata. I think pressure just decussates in the medulla oblongata. Pain decussates in the spinal cord. here's the second order cell body right here, and here's the second order axons going up here. Now here's the normal pathway here. Second order neurofiber goes up to the thalamus and synapses with a third order cell body in the thalamus. And that's true for all senses except olfaction. Remember, the third order cell body for sensory pathways is always in the thalamus. And then the axon from the third order goes to the cerebral cortex, to the primary somaesthetic cortex, and the somaesthetic association. You're telling you, oh, that's pain. You just injured part of your body, right? But there's a collateral here that leaves and goes up through the reticular formation into the hypothalamus and limbic system. And this is for an emotional response to pain. And it eventually goes up, also up to the primary somaesthetic cortex also. So they both go to the somatosensory cortex. One goes to the thalamus in the usual route, and one goes to the limbic system and hypothalamus, and is the emotional response to pain. That also goes to the cerebral cortex. Okay. And that's the intense pain in the beginning, the sharp, intense pain in the beginning. Okay. Then, now it's important to look at this slide here more closely and go over it because it's not in a book. I got it in a different place. But it's important. It should be in a book, but it's not. So here's the thing. One, nociceptor releases substance P into spinal interneuron. So here's the pain. Here's the nociceptor. You burned your finger. It goes in the primary first order sensory neuron to the second order sensory neuron, and it releases something called substance P. And this is really a pain neurotransmitter. Most pain neurons release substance P. I think it's a neuropeptide. And onto the cell body and dendrites at the second order neuron. And that goes up here too. Second order neuron transmits signal up spinal thalamic tract to thalamus. And then remember the third order neuron releases signals to the somaesthetic cortex, right? And said, oh, pain, I just injured my finger. Okay. Now over here, it doesn't show it, but here's the hypothalamus up here. This was that alternative route that bypasses the thalamus, goes up to the limbic system and hypothalamus, right? So then both the hypothalamus and cerebral cortex send information to the midbrain. This is number 4. Input from hypothalamus and cerebral cortex converges on central gray matter of the midbrain. Remember, that's around this, the cerebral aqueduct. I mean, that's a paraqueductal gray matter. That's pain, and that is the analgesic pathway. So then 5, midbrain relays signal to reticular formation of medulla oblongata. 6, some descending analgesic fibers. Now, analgesic means pain relieving, right? From medulla secretes serotonin onto inhibitory spinal interneurons. So here is 6, they're releasing serotonin onto these inhibitory spinal neurons. And this, and that turns on these inhibitory neurons, 7. And the these spinal interneurons secrete enkephalins onto the secondary neuron, secondary interneuron, secondary sensory neuron, blocking pain transmission by means of postsynaptic inhibition of second order pain neuron. So it inhibits the second order neuron. Also, other descending analgesic fibers synapse onto the first order pain fiber, blocking pain transmission by means of synaptic inhibition. Remember what synaptic inhibition is? It's a synapse on top of an axon terminal of a different neuron, and it inhibits, it hyperpolarizes the axon terminal. So when the action potential comes along, the axon terminal does not release neurotransmitter, which is substance P, which is the pain neurotransmitter. So it inhibits both the primary sensory neuron by presynaptic inhibition and inhibits the secondary sensory neuron by postsynaptic inhibition. So both of those inhibit the pain and lead to this dull ache, which is much less intense, rather than that sharp, intense pain. So this is because, like I said, once you figure out you're injured, and you get this sharp pain and you get injured, then what's the point of continuing having this real discomfort? You know you're injured, so to take care of it, now it just turns into this dull ache, so you know you get to take care of it. So because the pain message has already been received, so why continue it? Right? So we have a natural analgesic pathway. It's called spinal gating. Here it is again. Neurons in the medulla oblongata project the dorsal horns of the spinal cord to release serotonin onto spinal neurons. These secrete enkephalin onto second order neurons. Other branches of the neuron from the medulla oblongata inhibit first order neurons by presynaptic inhibition. It inhibits the secretion of substance P from the primary neuron onto the dendrites and cell body of the secondary neuron, and also inhibits the transmission of action potentials in the second order neuron. So that's the spinal gating. Okay, we've done it, general senses and spinal gating. Now we're going to move on to the special senses, which is the whole rest of the chapter. And so I'm going to take a break here and pick up the special senses with the chemical senses, gustation, and olfaction. So in the next video lecture. So this is going to be 203 senses 1. So I'll catch you on the next part of this chapter.